On here. Yep. Okay. Okay. Good morning, everyone. My name's Alyssa Jenkins. I'm a principal consultant with Mitsubishi Electric Power Products. I'll be the chair for this session called Grid Forming Project Examples. What is the industry learning from real-world deployments of grid forming inverters? So a little different topic, I guess, than all the planning the last couple days that's talking 10 years out. Now we're talking in milliseconds scale timeframe scheduling. So we have some good crew here. We have 4 in person and hopefully 1 online. We're waiting to get her connected. So we have Xiayao Zhou, Engineering Compliance Manager of the National Energy System Operator. We have Victor Velar Guerrero, Manager of Studies and Real-Time Simulation in Chile. So we heard a little bit about Chile. We'll hear some more today. We have Jing Wang, hopefully online from the National Renewable Energy Lab. And we have Liu, Manager of Transition Planning from the Hawaiian Electric Company. And then we have Slava Mileniskov, Technical Manager of ISO New England. So we'll get started with those. So who's first? Xiao? Xiao's first.
Hi, good morning all. So this is Xiayao coming from GB System Operator. I'm just today give a little bit of sharing a bit of information about our experience with grid forming development and some of the real project happening in the system. Yeah. So some of the background information, GB system. So we have about a 50 gigawatt system. Generation wise is about capacity is 120 gigawatt. So in the last sort of 20 years, we've been through the huge decarbonization. We have more and more renewable generation come into the system. We have a synchronous machine get decommissioned from the system as well. So we regularly operate the system with more than 70% of the renewable generation penetration level. And also that our peak record is somewhere around the 80%. So we have 80% renewable generation to feed the demand around peak level. So since it's not stopping there, I mean, the government have a really ambitious target as well. Just looking at by 2030, we have more and more renewable generations coming to the system. So that's around the offshore wind and onshore wind as well. And also the PV coming to the system. So we're gonna likely to have more and more renewable coming to the system. So our journey, I mean, for the grid forming really started around 2013. So when we initially did some study, we say, okay, if we keep on increasing the penetration level of the IBRs, at which point that we might run into a bit of a system problem. So we did some studies with academia, just keep on increasing the penetration level. And we started to find out if that the penetration level for IBR increased to 70% or 60 to 70%. So we are running into stability issue. And we're thinking, okay, what's the best way to solving that problem then? I mean, traditionally, we have already run the system with 100% of synchronous machine for many, many years. Seems that there's no issues about that. So if the IBR can behave like a synchronous machine, whether that problem can be solved. So that's the reason we kick it off some of the research project looking at can the IBR behave like synchronous machine. So we did quite a few research projects, and also that we did some demonstration as well, just to say, okay, if we can change in the control system, the IBR, whether that could behave like synchronous machine, then we can keep on increasing the IBR penetration level. And when we're talking to the industry, we're always running into this problem about industry keep on asking us to say, okay, from system operator point of view, if you having more and more renewable generation coming to the system, what exactly technical requirement you want the IBR to behave? And we also having the same question to the OEM as well. Just say, okay, if we having more and more IBR coming to the system, what kind of support you can give to the system that means we can running more and more renewable generation in the system. So that's actually in the end, we like to forming a expert group with different people from TSOs and generators and also developers working together to see whether we can come up with some of the grid code specification for the grid forming. So that leads to this three important document. I mean, around 2022, we actually developed a grid forming specification within the grid code. That's GC0137. So that to get approved by the regulator, system regulator of Jing. So we think I have to say this specification is non-mandatory. It means that the generator, if you want to behave like grid forming, you have to be, this is a technical specification for that, but it's not mandatory. It means that you don't have to behave like grid forming. You can still like operate like grid following. And after that, 2023 April, we also create a document that we call Great Britain's Grid Forming Best Practice Guide. That's just effectively give people a little bit more explanation on what it actually means for the grid forming, especially some of the information we put into the code. Try to explain a little bit more on that. So currently we are working with another document, which is further grid flow modification to looking at is a possibility we should actually mandate the grid forming capability, because currently it's not mandated, it's voluntary. So I mentioned about some technical development of the grid forming. As we all know that if you only have technical development, it might not be sufficient for people to actually adopting this technology. The reason being there's no sort of incentive for them to develop that technology. So we think actually it's fairly important, I mean, hand in hand, not only you have a technical specification, and you also should have a right market arrangement as well for people to be able to participate in the market using some innovative way. So that's why we kick it off this, we call Stability Pathfinder project. So the whole idea is that if the system operator, we can, I mean, doing some studies looking at all the future needs, and if this needs can be then clearly articulated to the market in terms of the how much we actually want and what type of the performance we actually want, then any of the generation have that capability or user have that capability, they can then participate into this procurement process, then providing the service to us, then helping the system to remain stable. So we run the 3 stages of the Pathfinder project, looking at a different area of the GB system. So we actually publish that information to the industry to say, okay, this is how much we actually want in terms of the inertia support and in terms of the system strength support or 4-level support, and by which year we actually want in which location. So any of the generator, if that they want providing the service to us, they have to meet in our grid forming specification requirement. So they need to be the grid forming first before they can participate into the market, and they can submit their price and also that technical validation report as well. So for us to choose actually which is the best solution for us to meeting all this requirement. So we've been running through 3 stages of the Pathfinders, phase 1, phase 2, phase 3. I think the phase 1 is mainly predominantly based on the mature technology. So we choose a lot of the SYNCOM to be connected to the system. Stage 2 actually is a more interesting one, which is more relevant to this talk. So we have about 5 projects, which is a grid forming battery, and also 5 projects, which is SYNCOM, wind bit connecting to the Scotland area, help us to manage the system stability. Stage 3 is or SYNCOM as well, it's just because at that time, there's not enough transmission capacity to accommodate more battery project. So that's procurement is looking at the longer term procurement. So normally people get 10 years contract to providing service to us. The reason being at that time, there's no existing asset could deliver that type of services. So we need to give people the certainty that they have a longer term contract so they can deliver the service for us. And we also thinking, I mean, for a lot of the existing asset, if they, especially the battery one, if they want to change in their control strategy, maybe they can do grid forming. If more and more people can actually do the grid forming, this means you have a more participate into the stability market or could potentially providing service to us. So under that condition that we were thinking about to moving away from longer term procurement process to some short term market arrangement. So that's currently we've been doing, rather than doing that or the longer term contract, we created what we called midterm market, which is year ahead market. It means that around year ahead time scale, I mean, for this year is that we procured around 2025. We started procurement process around 2025, and for the people to deliver in 2026. I mean, so any user, if they think that they can meet our technical requirement, they can bid into the market, then we can sign 1-year contract with them to providing the stability services for us. And so this is currently ongoing market development. I mean, in the long run, we were thinking about if more and more people having the capability, we might even shorten that time frame from the midterm market all the way to the short-term market, which is currently how we procure all the sort of frequency response market within the day-ahead time scale. So it could be a possibility we could include in the stability services into part of the day-ahead procurement process. So let's concentrate on our first battery project, the grid forming battery project under the procurement of the stability services. So this is a project commissioned I think March this year. So it's connecting to a Blackheath substation in the northern part of Scotland. So within that area, we have a large amount of the renewable generation concentration, that including all the offshore winds in that area, and also that we have a HVDC connected into that area as well. So in general, the system, the IBR concentration level is fairly high in that area. We don't really have many synchronous machine left in that area, and traditionally we have some stability in that area, stability issue in that area, especially around sort of subsynchronous oscillation. So the procurement was done a couple of years ago, and this plant was commissioned March this year. So it's about 200 megawatt battery, and they contracted. They're providing 380 megawatt second for the inertial response, and they're also providing the short circuit level support to the system as well. So I'd like to talk a little bit about the compliance process for this grid forming project, because that for grid following or any of the existing project for compliance process is fairly well established. So it goes through the different stages: simulation, factory acceptance test, and also the site testing as well. For grid forming, it's slightly different because of some of the functionality of the grid forming is going to be very difficult to test it under the sort of site commissioning test environment, especially if you want to introduce a frequency event, a rock-off event, or some phase angle jump event. Is going to be fairly difficult. So we're putting a lot of emphasis on the factory acceptance test, and so the people have to put in the inverter into the test rig and doing the different simulate different system event, like a rock-off event, like if you have a forced oscillation into that, what's the response of the inverter looks like. And we're using that information to validate the EMT model. I mean, the vendor provided to the system operator. And then doing a lot of simulations and making sure the whole plant's performance actually aligned with some of the factory acceptance tests. So in terms of the commissioning test itself, is fairly similar to the grid following one, because that it's hard to create a system event. However, we're putting a lot of emphasis on the site monitoring requirement as well. It means that they have to keep on monitoring the grid forming's performance, especially when there's a relevant event happen in the system, like a rock-off event or any of the oscillation event happen in the system. So for the model requirement is, again, this is the that's standard. So they have to submit to the both RMS model and also the EMT model that need to have a close alignment as well between these two models performance-wise. So I'd like to talk a little bit about one event happened in the system after the commissioning of the grid forming batteries. So we had quite a big generation loss event around March time. That's just after the commissioning of the grid forming batteries, but that's not related. So we have a 3 generation trip around very short period of time, around 15-second period of time. And in terms of the in-phase loss is around 2 gigawatt. So for the GB system, just for context, so the maximum in-phase loss we secure is around 1.8 gigawatt. So in theory, that's actually over what we normally secure for a security event. Some of you might still remember that we had a similar event about 2019. That's when we have a blackout in around London area. So amount of generation loss is actually quite similar, is all around the 2 gigawatt range. But you can see this time actually frequency behaves much better. But the main reason, because we only have one grid forming battery, so it's not related to grid forming battery. The main reason is that how we actually changing our frequency response product. So we now have what we call very fast frequency response. So people have to be respond to the frequency change within the 500 milliseconds. They need to be fully delivery that response within a second if they see the frequency drop. That's mainly done by the battery. So we have a huge amount of the very fast frequency response. So it means that the frequency drop for this similar generation loss compares to 2019, which lead to the blackout, but this time just a really small frequency drop. Anyhow, so that frequency drop from 51 all the way to 49.7. So it's still sizable. And we can see that how the grid forming battery behaves. So when you calculating the rock off of that event is somewhere around 0.1 hertz per second. So frequencies keep on dropping. One of the interesting things is that because all this faster frequency response from the battery, actually the speed of the frequency drop is getting very slow. And also the whole frequency nadir thing is going to be much higher than that without a fast frequency response. But if we're looking at grid forming batteries response, you can see they actually, according to the rock-off value, they're starting to providing additional inertia to the system. And we did the simulation results as well based on the model they submitted. We also using some of the inertia number they provided, just looking at if you're using a simple swing equation, what kind of the response you are expecting from the grid forming battery. And we compare that with site real-time information as well. As you can see, that everything aligns fairly well. So this means that this grid forming battery under this rock-off event behave like what we expected and providing the inertia and providing support to the rest of the system. So that's just the main event we had since the commissioning of that grid forming battery. At least that they been behave as we expected. I was hoping that in the future, if we have more event happen in the system, I'm quite happy to share some of the information with you guys as well. So that's all my talk. Thank you. Thank you.
Well, good morning, everybody. Well, I am from Chile, from the ISO of Chile. I will present our experience, especially with the reforming requirements proposal that we had there, and with the deployment plans of reforming in our power system. First of all is that last year we published a proposal for minimum performance requirement for grid forming. And this was based on international practices and standards, as well as EMT and hardware-in-the-loop testing made by us in our lab. We use the experience of the leading institution on this theme, IMO Unified NERC GPST Consortium. To support the proposal, simulations were conducted in the time domain with EMT tools. We use two models and a generic EMT model developed in collaboration with EMTP and EPRI, and the OEM EMTP model provided by a leading vendor. The product of this collaboration was a document by EPRI, NREL, and us. Regarding the hardware-in-the-loop testing, that was really a control hardware-in-the-loop testing because that was conducted using a real physical grid forming controller from a leading vendor. At the time of the requirement formulation, we had just one grid forming controller. Right now we have two. So we are retesting the typical test for grid forming capabilities, but with two grid forming controllers. We do that in our RTS laboratory. The structure of our document is a very typical structure based on, I say, the consensus about what performance must meet the grid forming technology. The first chapter is related to the core capabilities with the typical requirements like autonomous operation, island operation, with grid operation. This is important because in our system, especially in the north, we have very weak grid situations during the day. Maybe here I have to explain some characteristics of our electrical system. Chile is very long. We have a electrical system of about 3,000 kilometers from north to south. In the north are concentrated all the solar IBRs and some wind that export a lot of energy to the center load of the system that is in the center south of our system. In addition to the core capabilities already known for us, we incorporate the black star and sister restoration. This has been particularly important after the blackout event that we have earlier this year, where when black star and sister restoration was not so optimal. The document ends with our results on modeling and testing by us about this grid forming requirement, and we present the hardware-in-the-loop simulation results. Here I will go very quickly. I will present just two tests that in a way define what is a grid forming. The island operation, for this test, we use the test bench of AIMO, that is very well known. And this test obviously the results for a successful test must maintain a stable operation upon disconnection of the last synchronous machine. They must transition smoothly between grid connected and islanded operation. Well, the results of the EMT simulation are presented here. In red are the result of the EMT model developed with EPRI and us, and in blue are the result of OEM model, the actual OEM model from the leading vendor that collaborated with us. We can see here that the responses are very similar for both model, but the OEM model had a little bit better response, especially is instantaneous in his response. So maybe we have to work a little bit more with our EMT model. Related to the control hardware in the loop test, well, here we have just one controller, so we can't reproduce this exact test bench that used two reformer models. But anyway, in this case, the result was very similar to the EMT simulations. The result was stable and the response was almost instantaneously and according to the grid forming expected behavior. The other typical test that defined grid forming that we performed was the voltage phase jump. In this case, we use the AMO test bench. In this case, we look up that the grid forming must absorb or inject active or reactive power in response to the phase angle changes. In this case, we perform contingencies through 60 degrees, but in our system, maybe that number, that figure must change in our actual system. Here are the result of the EMT simulation with both tests, the generic or the developed EMT model and the OEM test. Well, we can see that for each phase jump, the result was stable, was expected behavior of grid forming. And the same for the hardware in the loop test with the real physical controller. In this case, the behavior was stable too, and according to what is expected in a grid forming technology. Regarding deployment plans, several years ago, we started studies for grid forming integration. We study on a large scale integration of grid forming in a scenario with 70% of solar and wind penetration. Just a note aside, last September, we reached 80% of wind and solar penetration based on inverters. In the figure, you can see the modeling of ENT software of our system, where we have more than 600 or 700 buses, more than 200 power plants, and thousands of control blocks in that system. So the simulation takes very long. The main conclusion of this study was that a minimum share of grid forming was required to keep the grid stable under extreme events. In this case was 15%, but this is a figure, a preliminary figure. Right now we are performing studies for a 90% IBR scenario by 2030, because, some of Chile objective is to achieve a full coal phase out of the coal power plants. Preliminary results are that the best reforming units exhibit comparable, if not superior or better performance to synchronous condenser on a MVA for MVA basis. This have implication, especially for tendering process of system strength and inertia services, especially because we're first tendering was just focused on synchronous condenser, but future tenderings will provide will permit grid forming competing with synchronous condenser. So how to compare that two technologies? It's not easy. When we compare syncons, we essentially compare short circuit provision, synchronous short circuit provision, or short circuit power, in a similar way that the Pathfinder project. Well, in this case, we think that obviously the grid forming solution must incorporate some additional parameter in the tendering process in order to do it more competitive and more in a more realistic way. What has been the industry and regulatory response to our reforming requirements? Well, has been very good. Both the regulator and the industry have responded very positively. In fact, the regulator that is in the process of updated our grid code that right now is very poor in requirements. In fact, don't incorporate any requirement regarding grid forming. Well, best projects in Chile are already adopting grid forming technology because they know that the grid code will change next year. As I said, the Chilean updated the grid code, and one of the principal issues here is that they will demand grid forming capability for all BESS connectors, new and existing. It's not clear whether the activation of the grid forming control mode will be mandatory for all BESS, or only those participating in services to provide system strength and inertia. The question here is that in strong grid areas with, for example, high ACR, grid forming may be not necessary, but in with grid areas obviously will be needed. And in this case, the question is, we as ISO can mandate grid forming a model control, or this must be preceded by a study determine the requirements and then a tendering process to participate in these services, in those services. Another important project we are very advanced in his development is actively promoting field pilots to validate the real world performance of grid forming in our system. We are currently in contact with several grid forming best projects. Already, we are in the final stages of approval for 2 pilots, 2 big best projects of both more than 200 and 400 megawatts. We are working on Black Star capability too, because, well, the blackout reveals some opportunities to improve our system restoration plans. So we saw grid forming as an ideal solution. This is a subject that I would like to incorporate here for discussion, and had to be with the on-site test requirement or procedure for connection approval. Obviously, the real condition testing in our system, our system, is key for new technology that is expected to be widely deployed next year. The questions are, should on-site validation use grid simulator equipment to reproduce with grid and low inertia conditions, and so-called hard test like fault right through with real faults, phase jumps. Here is a picture of a recent ISIC document that showed that kind of equipment, in this case for simulate wave grid condition. Or is sufficient to rely on natural occurring operational events in the grid. In Chile, we have a lot of changes in the operation during the day. At night, in the day, we have a dominated IBRs operation with big changes in frequency and with grid condition. In the night, obviously, we have a stronger grid. So maybe this is the approach. Maybe the approach could be mixed, because the grid simulator equipment is very expensive solution, at least for all the market participants. Another question to discussion is, are these hardware in the loop, control in the loop, laboratory or factory test sufficient for hard test in a specific system like the Chilean system? We currently have any certification process for inverters in Chile, or for reforming inverters or system. So this is an issue for us. is something like an irony that we have certification for, I don't know, refrigerators, iron machines, but not for grid forming technology. So we are now in an imminent rollout of grid forming because the best expected to be connected. There is a boom of BESS in Chile. Well, the principal highlights are for us, the grid forming technology is essential for enable our transmission process. We value that the EMT models with lab testing are necessary, and the on-site procedures for connection approval must balance accuracy and cost feasibility. Thank you.
She is? Okay. Yeah.
Jing, can you hear us?
Yes,
Perfect. You are more than welcome to share your screen.
okay. Share my screen. Give me 1 second. Sorry, Can you see my screen?
We can see the, there we go. Perfect.
Okay. Okay, thank you. Good morning, everyone. My name is Jing Wang. I'm from National Renewable Energy Laboratory. First of all, I would like to thank Julia inviting me to this talk. Today, I'm going to talk about our project, which is called Study the Control and the Protection Improvements for Weak Grid Area with High IBRs. So the goal of this project is to study the stability issue and the protection challenges with weak grid area with many solar plants. And we want to understand if adopting grid forming technology can solve those challenges or not. Since we are a little bit late in the project progress, so the grid follow inverter study here, and in our future report, I will show what we have done with grid forming. By the way, this project is funded by our utility partner and the NESO. Without further ado, I will start the presentation. So we have worked closely with our utility partner FPL and Florida Point and Light, which is the utility partner we collaborate. And GE Renewable is their grid forming and grid following inverter vendor. And at NREL, we have a team to do all the model validation, stability analysis, and the protection study. So this is a team. Now I will briefly talk about the project. So the diagram here shows you the weak grid area with the 5 solar plants, which is in the 230 kV transmission system. The line is about 100 miles away. That installed 5 solar plants, as you can see here. Each of them is 75 megawatt. And the FPL plans to install 2 bigger grid forming inverter. Each is 150 megawatt. For this weak grid area, they have experienced a lot of challenges. First, the SCR ratio is usually can go to below 1.5 PU. This is a typical weak grid area for them with a lot of solar plants. And they have already seen some oscillation issues. Additionally, the inverter has full rise-through problems, doesn't meet those grid requirements. And they also have the motor starting problems in this transmission line. Additionally, this transmission line, they also see the power quality issue and the relay misoperation. So those are the key highlighted problems seen in this weak grid area. So the project goal is to have NREL, FPL, and the GE working together to identify and predict the power system stability issue and the protection challenges with this weak grid area and find the mitigation solutions. So with that, the project has 3 objectives. First, we validate the vendor provided PS card, grid forming and grid following inverter against the hardware inverter reliable. So with this first step model validation, then we can have assurance the PS card model is very good for further study and analysis. The second objective is to understand the full ride-through behavior of this grid following, grid forming inverters, and also do the stability analysis to identify the issues and see if grid forming can resolve those issues. Third, we perform the protection study to see what are the challenge issues there and what are the proposed enhanced protection scheme there. So those are the project goal and objective. The next diagram will show you the technical approach. So first, we use the hardware inverter as a benchmark and test the how the PS card black box model match with the hardware inverter. We have both grid forming and grid following inverter we need to validate. We run through different dynamic studies such as LVRT, HVRT, Rokoff, impedance scan, and also phase jump, those typical tests people usually do for the model validation. So we have multiple iterations of changing inverter settings and the control parameters, and also DC modeling and the transformer. So after that, we finally got a very well matched model. And then we move to the stability analysis. We run through the full ride-through and see how the performance look like. And we also do the small signal and the transient stability study to identify the potential challenges and see if grid forming can be resolving those challenges. And then we run through the first study and see what are the protection challenges there. And then we propose the enhancements to increase the protection system reliability. So this is overall project approach. So next, I will briefly talk about the example results for the EMT model validation and the system stability analysis. This is performed by my colleague Xiayao. So this diagram shows the setup for the 2 megawatt. The bottom picture is the hardware setup, and the picture here shows the diagram. So we have the PV emulator in the DC as a DC source, and then we have the vendor grid following inverter. We have the transformer and also the grid simulator that we can apply a lot of different disturbance to do the test. We also have the very high sampling, 50 kilohertz sampling to get all the voltage and the current measurements and then do the processing. So this is the setup for the inverter, PV inverter model validation. And the results here, the example results here shows the different voltage dip test. For example, when we have the 30% voltage dip, you can see the dashed line is the PS card simulation results, and the solid line is the hardware inverter results. The PS card results align with the hardware inverter really well. Even in the transient moments, you can see here they match pretty well. And when the dip is removed, and then the post-fault behavior also match pretty well. So this is for the 30% voltage dip. And we also have 10% voltage dip. You can see the PS card results match the hardware results pretty well as well. So this is one example testing results. There are many others. Because of the time, I will just show another one, which is DQ admittance scan using the tool that Xiayao has. So we have a preliminary test. You can see before model revision, the impedance scan has some discrepancy in both magnitude and the phase angle. But after model revision, as I mentioned, including the DC transformer and also some inverter tuning, and then we finally make the impedance scan plot match pretty well. So this gives us assurance that the grid following inverter, the PS card model match the hardware inverter very well. So this is good news. Now we move to the full ride-through test because utility has this issue. So we run through the many different full ride-through, and we also did a 0 full ride-through. Luckily, those grid following inverter was able to sustain and ride through all the disturbance and meet the grid requirements. So that's what we find out. It's not a problem for this inverter. And then we run the stability analysis. We have the flat run to have all the 5 plants up online, and we figured out there was a issue with the 60 10Hz oscillation there. And after tuning by the inverter vendor, those oscillation is gone. Then we did the liquid operation with this side open, as you can see here. We find out the liquid instability of 8 to 10Hz oscillation, and you can see the plots here. They amplified and then sustained there. This oscillation is also aligned with the impedance scan results. So this is what we find out from the stability analysis. So those just some example results of the model validation and the stability analysis. Now I'm going to move to the for study and the protection evaluation. So this slide shows the methodology. So how do we do it? We first convert the reduce the Cape model to the PS card. We don't have the good grid forming model for the Cape software, so we have to do in PS card, and then so we first do the PS card model. There was a lot of challenges there because of the zero sequence impedance calculation. We have a report we are drafting now, so that report you can know what we do to do this calculation and model validation. And after we develop the PS card model, we plug in the OEM black box model, and we run through the normal and the N-1 contingency and also the IBR scenarios to see the to run through all the different scenarios. Then we did the playback in the RTDS and connect with the real FBR hardware relays configured with the field settings through the controller hardware load testing. Then we run through all the different fault analysis and summarize what are the challenges there, and then we propose the enhanced protection, including the customized logics, relay settings, and logics updates. And finally, if we validate those enhanced protection logics we propose to our partner. Our goal is to have the 87L differential element and also the local elements such as distance and the direction elements work reliably and make the decision within the first 4 cycles. So then it'll provide a reliable protection for this transmission line with so many IBR plans. So this is a methodology of our study, and the slide here shows our process to get the PS card model. So we actually start from the full Cape model, and then we did the reduction to include only the area with the interest, and then we further do the PS card model. For each model reduction and the development, we go through the full study comparison. So we run through single line fault, double line fault, and the single phase ground fault to see all the current level if they match or not. We also run through the trade and the data and to replay in the relay and then see if the model, the relay response match with the previous model. So after this comprehensive validation, we finally get the good PS card model that we can use for the simulation for the full study. And then the next slide show you the power system under study. So this is the model we use to do the full study. The bus 10 and the bus 12 are the transmission line connecting many solar plants. And for this study, we did the only one IBR plant that has a 75 megawatt PV and a 75 megawatt base, because that's the operational condition now. The other plants are under commissioning. So we need to do the first study for both lines as shown here. And for this PV and the base inverter, we have the preliminary study to see what are the potential challenges there. First of all, the grid following and the grid forming inverter both have very low fault current, and the fault current also very oscillatory, as you can see here. We talked to our vendor, they said this should be tuned in the future. And the more serious problem is both of them don't inject the negative sequence current. This will be a problem for the transmission protection elements that relies on the regulated negative sequence current. So those are the challenges there. For the study, we run through the normal N-1 conditions and the IBR only scenario. And we run the AG, BC, and the BC fault at a different location, 5%, 80%, and 95% distance. So this shows the system and the scenario we run. And we set up the laboratory controller hardware loop, see here, setup. As you can see here, we have the PS card run all the full study. We got the contrary data and replay in RTTS. And RTTS, we have all the CT, PT signal come out through the GTAO card, and then that connect with SCR 411L relay. And we got all the relay settings from our utility partner, and we use the 3 field events to validate the relay settings, CT-PT ratios to replicate the field event. And we did the auto scripting to run through all the testing. Due to the time, I will only summarize what we have learned from this study. So for all the 4 relays, they can operate reliably under normal and N-1 contingency scenarios. Under the IBR, the most severe scenario, the differential elements still operate reliably, but there are a few challenges as shown below. As you can see here, for the normal and N-1 scenario, the negative sequence current is very high, so those protein relay elements still operate reliably. But under the IBR only scenario, the negative sequence go up and then die down. The relay couldn't make the right decision. And you can see the 32QG, Z2G, those elements didn't operate. It goes high in the beginning because the negative sequence is high, but then it got disordered. So in summary, the problem are as follows. There's no negative sequence current injection. Direction elements are not operating correctly. Additionally, the mode element couldn't operate normally as well because of the low fault current. And the fault current is also oscillatory. They delay some relay elements to make the decision. The FID, fault identification logic, works reliably because we use the differential elements rather than the local elements. So this is a summary of the protection challenges. And then I will propose the solution to our utility partner as follows. First, we propose the enhanced protection. For example, we can use V instead of QV for ground directional elements priority, and also increase the threshold to block the supervision element that relies on the negative sequence. So this is for the ground fault. For the face-to-face fault, we design the customized logics as shown here, and we add the voltage supervised element that increase the reliability. And we have tested this enhanced logic. It works pretty reliably. Yeah. So this is first solution. Second solution is we advise our utility partner to work with inverter vendor to request and add the negative sequence current control in the inverter for both grid following and grid forming inverter, and make sure the IBR fault response is 2800 compliant in terms of magnitude. Negative sequence voltage needs the negative sequence. So I2 negative sequence current needed voltage 90 to 100 degrees and also settle down within 4 cycles. So this is the second solution. Third, we propose to use traveling wave-based protection to add running parallel with the 411 traditional phasor-based protection. So this is the proposed solution for the enhanced protection. And now I want to summarize the key takeaway from this project. So for the model validation, the grid following inverter match very well with the hardware inverter, and the stability analyze find out the 8 Hz oscillation with weak grid operation. Hopefully, this can be resolved with adding the grid forming inverter, and we also managed to do some tuning of the damping ratio and other parameters as well. And for the protection, the challenges are the low fault current and the IBR do not contribute the electric sequence current, but we can propose enhanced logics to solve those challenges, and also request the inverter vendor to add the negative sequence control in their controller. Overall, this project provide a feasible solution for industry to address IBR-related issue in control, stability, and protection. So what FPR faced today, the problem they have seen, I think many utilities will see in the future. So hopefully this project provides a lot of useful reference and guidelines for broader industries to solve those problems. So that's all from me. Thank you. Yeah.
Thank you, Jing.
Good morning, everyone. Thank you, Julia from UC for the invitation, and thank you, panelists, for the great presentation. I'm Li. I work for Hawaiian Electric, manager of transmission planning. Today in my presentation, I'll show some grid forming resource performance during various grid event. You may see these slides before or yesterday. Hawaiian Electric Company provided electric service to 5 islands in Hawaii state, covering 95% of the state population. All these 5 islands have their own isolated system. So largest system is Oahu. Peak load right now is around 1.2 gigawatt. And then Maui Island, Hawaii Island, the 2 islands, similar degree, around 200 megawatt peak load. And Molokai and 9, there's 6 megawatt, maybe microgrid. The net zero target by 2045, 100% reduction of the carbon emission, and by 2030 reach 70%. Right now, I think, yeah, we are working very hard toward that target. Regarding the grid forming projects, yeah, so I think everybody know that we have transmission level interconnected grid forming projects. So the coupled energy storage projects, 138 kV interconnection. It is 135 megawatt 4-hour regular time shift battery, and then there's another 50 megawatt 0.5-hour duration fast frequency response unit integrated inside the facility, and the owner or developers Plus Power and the OEMs Tesla. We also have in the same system, Oahu, we also have sub-transmission level interconnected grid forming facility. There are 46 kV interconnected right now. The contract capacity at the POI is 42 megawatt. It's a PV paired with battery AC coupling, 4-hour BESS module, and the owner is Ameresco. The GFM battery OEM is Tesla. Yeah, so all the GFM function provided by the battery inverter. The GFM projects that will be commissioned in near-term future, which means next year or the year after next year, yeah, we have 2 more sub-transmission interconnected grid forming projects on Oahu system. So they are relatively smaller, 7 megawatts and 30 megawatt, this kind of size. and the developer AES and the OEM different. They're Hitachi, GFM projects, and these two projects are DC coupled. Yeah, DC coupled PV parent bus. And then Maui, we will have our first transmission connected grid forming projects in a couple of years. They're standalone battery, 4 hours, and 40 megawatt. So OEMs, also Tesla, so developed by HECO. Right now we're doing a wrapping up stage 3 RFP system impact study. In this RFP activity, so we, I think we procured 126 megawatt IBR projects for Oahu. All of them are grid forming projects, PV paired with battery, AC coupled, and Maui 60 megawatt, the same PV paired with battery, AC coupled, one AC and one DC coupled. And then Hawaii Island, 86 megawatts projects, DC coupled. Yeah, we're very excited to see these projects. Hopefully they'll get commissioned. I think within 3 to 4 years, according to the schedule. Meanwhile, we are working with commission right now, try to get our IGP RFP first round approved in this year. Hopefully, in the future couple of months. And in this RFP, this is our first time we tell the public that we need to procure more GFM for stability purpose. So right now target is for Oahu is 350 megawatt GFM projects, and Hawaii Island is 150 megawatt. We will do a separate RFP for Maui very soon. Yeah. So all of our islands will need grid forming projects to enhance our stability performance. This is the first event. I think you guys may saw this plot several times. Yeah, this is a generation tripping event. It is around 15% of the system net load get tripped from a tripping of one synchronous machine. And in this plot, the blue curves is our KES facility response to this event. I think at that time, this is the only grid forming project online. And then the brown curves is the system frequency. Immediately after the generation trip, there's no system fault. So this is a pure generation trip. We see very strong response coming from KES facility. Yeah, at the very beginning we thought, oh, that's probably triggered FFR. But when we align the megawatt response with the system frequency, it actually is not. It's a grid forming response to this frequent generation trip. And we do see this immediate response from KES facility help reduce frequency change. And once frequency hits the threshold, which is 59.4 hertz, FFR module gets triggered. So we see another jump on the megawatt. And then after that, frequency start recovery, totally turn the direction. Yeah, so in this around 10 seconds curves, we see first the GFM response, and then it's FFR together with the GFM response. I believe PFR response also kicked in. Yeah, but it's blended. I want to say it's blended. This is second generation trip event. The magnitude of generation trip is smaller. It's around 6% of time, 6% of the system net load. The purpose of this slide is to compare different resource response. So the red curve is a system frequency. The axis is on the right side frequency axis. vertical axis. It was not reaching 59.4, so there's no FFR triggered. The gray curve, that's the KES response. The dashed curve is ideal primary frequency response. The blue curves is a response for this event from a GFL resource. It aligned with PFR response very well. And then the brown curve is a machine response. So we can see the beginning inertial response and then very slow PFR response coming from this machine. I think this gives us a really good comparison about the performance of different kind of resource. And yeah, so apparently this GFM response is very big, and all this response are described as a per unit of the contract capacity on the left-hand side of the vertical axis. This is about a fault, so there's no generation trip. This is another event happened in Oahu. It's a transmission fault. The fault happened on the east side of Oahu, and the resource are showing this slide and the following slide are all on the west side of Oahu. So first of all, it's not a very severe event. There are impedance involved in the fault, and then it's an unbalanced fault, line-to-line fault. Left-hand side is a grid forming 138 kV resource response curves. The top one is the voltage measured at a 138 kV side POI. So you can see the two-phase voltage get reduced. I think the fault happened between those two phases. And then third phase looks okay. The middle figure is the per-unitized instantaneous current response from this resource. And the lower figure is the P&Q measurement for this resource. Sorry that the time horizontal is not that aligned among these three curves, but I think the performance is very clear. And for the comparison, for the sake of comparison, the right side I put the synchronous machine response. We also have DFR on some synchronous machine, but the DFR monitor on the machine terminal side, so it's not 138 kV side. So the voltage curves looks a little bit different. Maybe we can focus on the current curve, the instantaneous current curve. I would say this two resource, the instantaneous current response, they're very similar. Yeah, they are very similar. And when we look at the power measurements for the response, we can see during the fault, both resources provide very strong support, also including the recovery stage and the post-recovery stage. For the grid forming resource, it's very, very stable, the whole performance. We do not have monitors inside of plants, and we don't know what's going on really inside the plant. So this is so far what we can share. Yeah, we need to talk with the developer and OEM if we really want to look inside a plant. The next slide shows the comparison between the GFM resource and the GFL resource. The GFM resource is the same resource. The GFL resource is also a transmission connected GFL resource. There's a standalone PV resource, and the event happened during daytime. So I think we can tell the huge difference regarding the current response from two resource, not only during the fault, I think especially post the fault clearing. So from high level speaking or analysis, we can see the GFL resource, this one, it does not show or shows very, very limited support to system stability during fault and the post-fault recovery. We do see, current increased during the fault. But when we look at the power curves, we see megawatt power drop, as well as the megawatt drop, and especially at the time during the fault, post-fault clearing during the recovery stage. Yeah. So imagine if all the resource in the transmission level, behaves like the right side of the figure, in 2045, I think that could be a really, really bad event. And this is just a very common line-to-line fault. Maybe this is a tree branch following the two phase of the transmission line. Yeah. This is the 46 kV GFM resource, and the 46 kV GFL resource. So the GFM one, the response similar to the 138 kV, the GFM resource response. So again, we see strong support to system stability and also strong support to the recovery from the fault. For the GFL one, yeah, I would say we see maybe some partial momentization, this kind of thing happened inside the plant, but during the fault, both active power, reactive power go to near zero, and the current looks like there's maybe some phase angle issue maybe caused by the PLL thing. But the good thing is after fault clearing, they recover pretty fast. They can quickly recover to the pre-fault generation level. Not every GFL resource can do that very robust and fast recovery once fault is cleared. But yeah, but we do not see any support of the system stability during fault. Yeah, I don't think we can expect this kind of response to help our protection. This is my final slide, and this is from simulation. This is not from real system event. I want to use this slide to make point that we need GFM, and more importantly, the GFM the control need to be tuned. We spent a lot of time during our interconnection study to tune GFM to make a response, reach our expectation, reach our requirements. So left-hand side is if we do not tune GFM, or if it does not tune well, you can see during the fault, the frequency dropped and the response of the resource jumped very high. But once fault get cleared, the response from the resource go totally south. So we don't want to see when system try to recover from a significant three-phase ground fault, and this resource takes tons of power from system. Yeah, this could make our frequency nadir really low and the frequency recovery really hard. And then we work with study consultant and then our OEM project developer try to tune this resource, and the performance can be improved a lot. Yeah, so yeah, we just want to make this point, and yeah, I think that's all. Thank you, everybody.
Okay, good morning. I'm Slava Maselnikov. I Sony England, and my title could be confusing because it's normally belong to IT world, but my expertise in research and development in power systems. There are a lot of publication related to performance of IBR in very simple systems. It's a lot, but much less published on how that will impact bulk power system if you have massive replacement of traditional generator by IBR. So that is research, that presentation is related to numerical study intended to answer three main questions. how system dynamic properties change with large penetration of inverters, how the frequency nadir is impacted, and what is the reasonable metric to monitor acceptable system behavior. So NREL mini-WEC system was used. It's 240 bus system with more than 100 synchronous generator. You see dynamic properties of the system are typical: structure of oscillation, inter-area, local oscillation as shown by eigenvalues is pretty much typical in base case. So for modeling inverters, grid following inverters were modeled by normal REC G, REC C, A, and C models. For grid forming, two models were selected: A1 and B1, which droop control and virtual synchronous machine. So for the study, it was type of Monte Carlo simulation when an arbitrary number of generators were replaced by inverters with random combination of grid forming and grid following. And also important one is headroom for control on grid forming inverters was varied from 0 to 10%. So results of this study as good as positive sequence model of inverter is good. So that is a limitation. So the first step of study was to find to evaluate what would be how dynamic properties of the system will change. Basically, that is eigenvalue type of analysis. So virtual synchronous machine, actually model of inverter, is intended to replicate properties of synchronous machine. And this simple test actually confirms that. So if you change parameters of inverter, you can easily control damping and frequency of oscillation and even create instability. But the key question, that is good because it's really intention and of initial intention and result are consistent. But from another side, if we are replicating property of synchronous machine, at the same time, there is a risk that we will replicate interaction of synchronous machine and bulk system, leading to creation of inter-area oscillation, which is a really undesirable property, which require simulation of entire bulk power system as a whole, and that is really undesirable. So that slide shows what would happen with the dynamic properties of the system if grid forming inverter will replace 25, 50, 75% or 100% of generator. As you can see, that results is very optimistic. So what does it mean? That damping of all modes increased very significantly. And as soon as you approach to 100% of penetration, actually all oscillation disappeared. And for this modeling, I have to say that parameters of grid forming inverter were exactly the same for all inverters without any modification. Like we take parameters from on-the-shelf model, apply it to the system without any variation, and results surprisingly good. Okay, this slide shows what would be the difference between modeling of grid forming inverter if it's virtual oscillator or is it just droop-based control. And the right table on the right side shows that practically it doesn't matter because structure of oscillation remains the same and property is the same. The more you have inverters, the better dynamic properties of the system are. And that slide shows confirmation in time domain of the same results. On the top, that is a picture of transient when you don't have inverters. On the left side, one model, and another side, left side, another model. From the top to down, it's 25%, 50, 75, and 100% inverter penetration. And those results confirm small signal analysis, showing that if you increase the number of inverters, then damping is increasing and oscillation practically disappear. So, and again, it's extremely positive result. So next set of calculations were related to frequency response. And For modeling, what was used as a fault, the same fault type of calculation. It's stripping of generator for 1000 megawatt. It's approximately 3% of the total capacity in the system. And what was monitored in the study is variation of nadir in frequency. So bottom line shows the formula, meaning that if resulting nadir became positive, that means inverter do not good job. They actually reducing nadir of frequency. And that slide shows samples of what type of transient could be expected. On the top right corner, you see transient when there is no inverter. So you see a lot of oscillation with different frequencies and damping whatever was expected from eigenvalue analysis. On the left side column, it shows transient for different penetration of IBR and relatively small headroom for control, cumulative headroom for control. Top figure show traditional nadir, which is happening within 3 to 5 seconds. Middle plot show delayed nadir, which you typically don't see in a traditional power system. And bottom picture show instability when frequency is drifting gradually to unacceptable level. On opposite, on the middle vertical plot, you see about the same penetration of IBR, but which is much higher total megawatt headroom for control. And result look like almost perfect. Okay, and this picture show results of statistical run. Every dot on this plot is single transient calculation analysis, and color-coded points show deviation of nadir comparing to case when you have only generators. So reddish type of curve means that IBR deteriorate nadir of frequency. And from this plot, for this calculation, only grid-forming inverters were modeled in the system. And horizontal line in the graph show percentage of IBR penetration. So all negative results, which are highlighted reddish, are located in the area where you have a lot of IBR with relatively small headroom for control. That is the main conclusion. And this slide shows two typical pattern for that statistical run. On the top graph, illustration for a situation when deterioration of nadir is caused by low total megawatt headroom for control, as it's shown over there. So this is two cases with approximately the same penetration of IBR, like 58% of over there, but very different total headroom for control. And lack of headroom of control result in significant reduction of nadir. On the bottom line, you see another phenomena, which is showing locality of headroom. On horizontal axis on this curve, it's electrical distance from generator was stripped as a contingency. So if you have sufficient amount of megawatt headroom for control in close proximity to that generator, it will greatly improve nadir of frequency. And opposite, if there is a hole, I mean, lack of total megawatt headroom for control, that result in deterioration of nadir. Next set of results was related to if we combine grid following and grid forming inverter together in the system. And that is picture where all results shown in the same way. Each point is a result of one transient. So axes are percentage of grid following and grid forming IBR in the system. And a picture looks like complete mess. And the reason for that is because that is two-dimensional graph showing results of approximately 4-dimensional results when you see different penetration of IBR, different headroom, and different allocation across the system. So that graph roughly explains main trends, what is happening in the system. For example, on that area, on the top left part, a lot of red dots, and that means it's a reflection of pattern when you have a lot of grid following inverters and lack of megawatt headroom for control in grid following. This area here show that despite you have a lot of grid forming inverters, still you may have instability because there is a lack of megawatt headroom for control. And it looks like there are some outliers, like over there. It's very low percentage of inverters in the system, but you have instability. But that is specifically cases related when you have grid following inverters located and location with a low short circuit ratio. Okay, that graph illustrates typically the same result with different metrics. Horizontal axis show short circuit ratio where inverters are located. On the top graph, that is statistic for all unstable cases. And pattern is pretty clear. Blue bars show total amount of megawatt for grid following inverters. And if you have prevailing inverters with grid following control, you have instability. On the opposite bottom plot show if you have proper combination of grid following and grid forming inverters in location with low short circuit ratio, stability is preserved. And that graph shows the same statistics, but with different metrics, which is proximity or distance of the inverter from the generator which stripped during contingency. Logic is absolutely the same. So if you have a lot of grid following inverters around, that is resulting in problem instability, and opposite. If you have proper combination of grid following and grid forming, you have good results. So in general, observations are the following. If you massively replace traditional generator by grid forming inverters with in proper way, results are very optimistic, at least based on this study. And what does it mean? You drastically improve dynamic properties of the system and improve stability and frequency response. And specifically, what does it mean? So practically elimination of inter-area modes, drastically improvement of damping of oscillation, and system response became localized. And that is very important because it may have very significant influence on the type of studies we do. Because before we need to study whole system in order to reflect properties. If this conclusion is true, then you have drastically reduced size of the area. And another observation is, as I said earlier, all parameters of grid forming inverters were exactly the same, no variation across the system. And that is very good indicator that you don't need to be worried about tuning of parameters of inverters. Can take universal settings and apply it like on-the-shelf solution for any location in the system. So, and what does it mean, right or proper replacement? That means practically two things. You need to have sufficient total megawatt headroom for control, and it should be uniformly allocated across the system. So regarding grid following inverters, yes, they could be in the system, but with proper combination with grid forming inverters. And what is the reasonable metrics based on this research is basically the only one parameter. You need to make sure that you have enough sufficient amount of total megawatt headroom for grid forming inverters in the system. And that should be for system-wide and locally. And currently, a lot of research and publication related to system inertia is monitoring parameter for system health. At least that type of study showed that that parameter is really irrelevant, because really what is important, how much headroom for control you have in the system. So again, results are very optimistic, and they are valid as long as RMS model for inverter is correct. So thank you for listening.